We analyze real world situations and kind of interpret it just like by looking at the numbers. It's not just like, oh, we get a number, like that's it. We can actually like apply it to real world solutions and see like if there's a relationship between two things and how that impacts the real world. So I think that's good. Like when I'm doing my projects, I see like, oh, this is how I could apply this if I was in this job, or like, oh, I see why we compare these two things. It's not just, oh, these concepts and just like putting it back on a test. So I think it's really good.
We have like lots of discussions and lots of movement, working in teams. She's able to make us like actually work in teams. I don't know. She makes us actually work in teams. I don't know how that works. I like having the vertical whiteboards too.
You like using the whiteboards? How come?
Well, just you get a like different environment. You get to stand up. Also, you're like working together, and it's a bigger space, not just on your graph paper.
Yeah. Do you feel like you're learning?
Yes. Yeah.
And you feel like high school is helping you to figure it out on your own? What do you think about that?
What do you mean?
Like, do you like that better? Do you like to figure it out on your own? How come?
Because I actually learn it.
You feel like you learn it better? Okay, all right.
So after high school, I went to UC Davis initially for chemical engineering, and then transferred to UCLA for chemical engineering after my sophomore year. So I did 2 years at Davis and then 2 years at UCLA. After completing my coursework at UCLA, I decided to continue, and now I'm doing my PhD in chemical engineering, still here at UCLA.
What kind of math experiences do you think are valuable for the incoming students that you're teaching?
I think one of the big things is the ability to problem solve, to see a problem and to think about it in a mathematical sense, which is kind of step one to applying anything in the scientific world, is figuring out how you can describe what's going on. But the ability to visualize and understand what the sort of mathematical concepts, just like what a plot is, what solving for a variable really means. There are a lot of students who can solve a derivative very quickly, but don't understand why or what it means or what it's for. And being able to visualize that on a graph and what it looks like in the real world all at once is very, very helpful. And so one of the things that we really emphasize is drawing and visually describing your solution and why do you care. And I think one of the big drawbacks in my own personal education was that whenever we did this sort of visualization, there was only one ever. It was either like plot it or draw the picture, never all at once, which is something that I didn't really think about until I started teaching the fluid dynamics class. They're not always all important, but sometimes certain ones are and certain ones aren't. And being able to think about which ones are is a very, very important skill, that I think just makes it easier to contextualize, understand, remember the math concepts that you're working with. Then you get to a real world problem, which is the same exact fundamental skill, and you don't understand why it's important or remember that it's the concept that you need. Come from doing it yourself, right? You can't really teach problem solving without, I mean, you can teach a little bit, but the students have to do it themselves in order to learn it. You can't just show them how to do it and then they'll never learn problem solving that way. So it becomes pretty clear partway through who has an idea, the conceptual knowledge of what those numerical methods, what the math behind their equipment means and all their work. And the people who do have really, really great results, and what they do makes sense and they can justify it. Sometimes obviously they look at something that doesn't make any sense, but then because they understand the concepts beforehand, they have some idea of how they got there and why it's wrong.
I recently graduated back in August with a Bachelor's of Arts in Computer Science, and I am currently interning at General Atomics doing robotic simulations. Different way of problem solving that I learned. Not necessarily 100% in my math class because it was mirrored in my high school computer science class, which was also seeded with a ton of math in there. I've found applied math to be the way that I learn it the best. So physics, computer science. If I'm using math to do something, that helps me understand how that math works, and it gives me tangible results of what's going to go on. Anything to do with rote memorization, I wasn't helpful for me. Nowadays, I can just pull it up on my phone, like, oh yes, I forgot the double angles. That's a double angle right there. Let me look up the double angle rules and those sorts of things. It's unnecessary at this point, and I've completely forgotten it. Applied mathematics has made me more interested. I know I've mentioned that doing physics and graphics where I see the functions doing what they're doing and I'm making my own making math spin in my own way that it makes something pretty, or makes my submarine actually stay neutrally buoyant rather than floating up to the surface. That's definitely helped